So this is the one-dimensional infinite square well, very common problem in introductory quantum mechanics. But we're going to do something a little bit different. We're going to look at solutions, which I've already gone over the solution to this, so I don't want to go, I want to start with the solution and then plot some stuff. Okay, so let me just give a quick, very quick and brief overview. So this is what we have, a one-dimensional square well such that it starts at x equals 0 to x equals a, and this side is infinite potential and that side is infinite potential, and that means that the wave function can only exist here, and that these points have to be continuous with a zero wave function over here, such that we get something like that where it has to match. And with those boundary conditions, we end up with solving this differential equation, which says psi, the wave function that depends on x and t. We have the partial of that is equal to the second partial with respect to x in one dimension plus the potential, and the potential is 0 in here. So with that, we get the following solution. First of all, we get this. We can split this into a space part. I use lowercase psi, and a time part, e to the negative I e n t over h bar. And it turns out that the solutions are quantized. Only certain energy levels are allowed, and these are my allowed energy levels as a function of n equals n is 1, 2, 3, and 4. And then this is the spatial part of the wave function. A lot of times people just plot the spatial part of the wave function because this doesn't really do much. And in fact, if I plot the full function and I plot the probability density, we can find the probability density as the complex conjugate of the wave function operating on the wave function. Then let's do that and show that this is if I have a normal wave function for n equals 1 or any n, but I only have one energy in there, I get a stationary state that does not depend on time. So let's just put this together with that, and I'm going to take the complex conjugate, so I get p. Actually, I'm going to leave it like this. P is going to be equal to this. The wave function here has no imaginary numbers in it, so I don't have to take the complex conjugate of it. I just need to take the complex conjugate of this, so instead of minus I, I'm going to put plus I. So I get psi of x e to the I e n t over h bar. And then I'm going to take just the normal wave function, which is psi of x e to the minus I e n t over h bar. And I can simplify this. I can combine these two together. I get psi squared. And then I have e to the I e n t over h bar, e to the minus I e n t over h bar, and these two cancel to give me 1, and I just get psi squared. So there's no time dependence in here, and it just stays. So if I plotted the probability as a function of time for e equals 1, it would just look something like this. That's it. Okay, but it's possible to have a linear combination of more than one state. So I actually can write this. Psi of x and t is a linear combination of over n from n equals 1 to infinity. It can be Cn, some constant, psi n of x t. Oops, I don't need that. So I can take the first energy level solution plus the second energy level solution, and that could be a solution. And I would need some constants out front, but we can just either pick those as long as they're normalized, but whatever. And so the question is, what would that look like? And it turns out that's a non-stationary state. And so I want to plot that. So let's do the following. Let's say that we have two energy levels, 1 and 2. So I'm going to say psi of x and t is going to be equal to C1 psi 1 e to the negative I e1 t over h bar plus C2 psi 2 e to the negative I e2 t over h bar. So here I'm using energy level 1, here's energy level 2. And so I have a linear combination of these two, and we want to plot that. I'm going to pick values for C1 and C2, but let's just see what happens when we find the probability density first. Okay, so P is going to be equal to, I'm going to drop, no, I'm not. So P is equal to psi star psi. So that's going to be the complex conjugate of this. It's going to be, let's write that as C1 psi 1 e to the I E1 t over h bar plus C2 psi 2 e to the I E2 t over h bar times, technically operated, on this, as it is, C1 psi 1 e to the negative I E1 t over h bar plus C2 psi 2 e to the negative I E2 t over h bar. Okay, so now I have to multiply this out. Let's do the simple terms first. So I can take this times this, and that's the same thing. I already did that, right? Because now I have e to the I E1t h bar e to the negative I E1t over h bar. So those two are going to multiply by each other and give us 1. So I get C1 squared psi 1 squared. That's this term, these two. And these two are easy also, because the same thing happens. I have e to the I E2, e to the negative I E2 t over h bar. So those two multiply together to give 1. So I get plus C2 squared psi 2 squared. Now, but I have some cross terms too. So let's write out the cross terms. So both of them, I'm going to have C1 psi 1 times this. So, and then I'm going to do these two. And both those have a C1, C2, psi 1, psi 2. So I'm going to factor that out. C1, C2, psi 1, psi 2. Right? They both have that. Now I can just deal with the exponentials. So I'm going to multiply this times this, and I get e to the, okay. Now, actually, let me put it in the same form I had it before. Where'd I put it? I want to use the same form I did before. Sometimes I work out these things beforehand. I don't know if you knew that, but that is indeed true. How did I do that? I called this a negative I. Okay. So I have e to the negative I, and I'm going to get this multiplied by this. So if I have the negative I, factor it out, that one doesn't have a negative I, so that's going to make a negative e. So I'm going to get E2 minus E1 t over h bar. You see how that is? I'm adding these exponents, and then I'm factoring out the negative I. And so the only difference between these two exponents is E1 and E2. And one's negative and one's positive. So that's why I have this E2 minus E1. I want that E2 minus E1 factor in there. And then I'm going to do the other cross term, which is this times that. Now in this case, I have E2 as with the positive I and E1 with the negative I. So I'm going to get the opposite. So I get plus, I do get the opposite, right? Yeah, plus e to the I E2 minus E1 t over h bar. Yeah, that's parentheses right there. Okay. So I have the stuff that I expect. That's easy to deal with. And then I have the cross terms. And they're not difficult to deal with. But let's just rewrite this as something a little bit simpler. So I'm going to say theta is equal to E2 minus E1 t over h bar. So in that case, I want to simplify this term right here. That's going to become e to the minus I theta plus e to the I theta. And there is a formula for this, but I'm going to work out the formula in a longer way. I'm going to use the formula, the Euler formula, e to the I theta equals cosine theta plus I sine theta. So if I have that here, let's put in, if I put in minus, I'm going to put in minus theta. So let's write this e to the minus I theta plus e to the I theta equals e to the minus I theta is going to be cosine negative theta plus I sine negative theta. And now I'm going to have to do it with the plus. So I get plus cosine theta plus I sine theta. Now, if you remember anything about your trig functions, you remember that, and it doesn't hurt to draw a little triangle here, right? Here's theta. And so sine is going to give me the opposite adjacent. So sine is right here. What if I put in negative theta? Well, negative theta would be like this. So my opposite, which is sine, is going to give me a negative number. So sine of negative theta is negative sine of theta. Cosine of negative theta is cosine of theta. Okay. So cosine of theta and cosine of theta, these are both cosines of theta. So this is going to be equal to 2 cosine theta. And then I have minus I sine theta plus I sine theta, which is awesome because now I don't have an imaginary number. Okay, so now I can put this back in to my full expression. So I'm going to write this whole thing out. So let's write this right here. So I get psi star psi is c1 squared psi 1 squared plus c2 squared psi 2 squared plus c1 c2 psi 1 psi 2. And then this whole thing was just cosine of theta, which is going to be 2 times cosine of, let's put it in parentheses like this, e2 minus e1 t over h bar. So that's my function, and it depends on both space and time because these are space things. Let's write out everything. And in fact, let's do it a little bit further. I'm going to pick values for C1 and C2 that I'm pretty sure work. C1 is the square root of 3 over 10. C2 equals the square root of 7 over 10. I'm pretty sure that will make it normalize such that if I integrate this from 0 to a, I get 1. That's important. But you see here that I have this part that depends on time and it's not going to be stationary, and I want to plot this whole thing. So let's just write this out as much as we can. So I'm going to leave the C1 squared as this because I know it's a constant. C1 squared, and then psi 1 squared is going to be, remember, put it up, psi of nx, square root of, I already have the coefficient up front. Sine n pi x over a. So I'm going to square that, so I get sine squared of n, which is 1, so pi x over a. And now for that one, I get plus c2 squared sine squared, and that's going to be n, which is 2 pi x over a. Then I get c1 plus c2 times c2. And then I have the product of these two. So I get sine of pi x over a times sine of 2 pi x over a. And then I have another 2. I'm going to put the 2 over here. And then I have cosine of e2 minus e1 times t over h bar. Now, I want to plot this. I'm going to have to find E1 and E2. So E1 is going to be equal to pi squared h bar squared over 2ma squared. And then E2 is going to be 4 pi squared h bar squared over 2ma squared. So I have everything I can do to make a graph. Now, we can, this is where you get into the part where I want to actually graph it and calculate stuff. Units, right? What do we do about units? So I'm going to say, what if I put h bar equals 1, m equals 1, a equals 1. I know that's boring, but then I get E1, I get it simpler. E1 equals pi squared, right, over 2. E2 equals 4 pi squared over 2. So 2 pi squared. And now I can start doing things. This is going to be 1. Let's just do that. If it turns out poorly, it turns out poorly. I'm fine with that. But I want to plot this. So I'm going to switch over to Python. I'm going to use Trinket GlowScript. I'm going to use GlowScript vPython in Trinket to plot this because I find it's easier to make animated graphs. So let's just see if we can get this to work. Move over here to Python, which I already have started up. Computer view. Okay, so the first thing I'm going to do is to make a graph. So, I should put my constant. I'm going to make the graph first. G1 equals graph. X title equals X. Y title equals P, right? It's a probability density. Let's give it some dimensions too. X, or say width equals 500. Height equals 250. That way, because when I'm plotting it in this, it's going to be a little bit smaller. I don't want it to be too big. That's fine. Now I need to make a graph that I'm going to plot. So say F1 equals G curve, color equals color dot blue. And G curve is a built-in function in the Glow script. It just means that I'm going to plot data points and connect them by a curve. So I want to make an animated graph. So the first thing I'm going to do is to plot the total probability density at t equals 0, and then I'm going to change t and like that. So let's start off with our constants. A equals 1, m equals 1, h bar equals 1. I know that's boring. C1 equals square root of 3 divided by 10. C2 equals square root of 7 divided by 10. Let's calculate E1. E1 is going to be, I already said it was, what did I say it was? Pi, well, let's just write it out. Pi squared times h bar squared divided by 2 times m times a squared. I have a, yeah. And then E2 is going to be equal to the same thing with a 4 in front. Okay. Let's write, I'm going to make a function just because I want to. So let's make a function for calculating the probability density. So I'm going to say def p, and I'm going to pass to it x and t, and I'm going to return the probability density. So how do we calculate that? Now I just need to type in my equation. So I'm going to say, let's just call it p temp, just in case I need to do anything to it. I'm just going to type out this equation. C1 squared times sine pi times x over a plus C2 squared times, oh, that's sine squared. This is complicated. Sine, that's what I should do. Let's watch this. Psi 1, let's just do that. Psi 1 is going to be, I'm trying to decide if I should include the C. Yeah. C1 times sine of pi times x over a. Psi 2, yeah, that works, is equal to C2 times sine of 2 times pi times x over a. And this is why it's great to make a function, because I can break these calculations into more manageable parts. So now I can say p temp is equal to psi 1 squared plus psi 2 squared plus psi 1 times psi 2 times, now I have the time part. And that time part is going to be cosine of E2 minus E1 times t. I'm going to change that, TT, divided by h bar. And so let's go up here and call this TT and XT for temp. So down here, I'm going to change these all to temp. I don't want to get them confused with global position variables. I think that's good. TT and XT. Okay. That's my temporary probability density, and that can return P temp. So return a single value. Let's just see if this works. Let's see. Let's put in, if I put in x equals 0 and t equals 0, it should be 0, right? Because that is at the edge of the thing. The wave function should be 0. So let's just say print p 0, 0. And I'm scared. Let's see. Let's call this non-stationary 1D well. Save it. Object promise. Okay, so that didn't work. C1 sine pi xt. Let's try this. Print E1. Okay, that worked. Let's print E2. Okay, that worked. Okay, let's go up here and copy this. And print, let's say xt equals 0, xt equals 0, tt equals 0, and let's print this p psi 1. I bet you I typed something wrong somewhere. Okay. Line 16, oh, tt equals 0. If you get an error, that's actually a good thing. So then let's try this one. And run that one. That's 0, 2. Okay. Now let's print this. Let's do this. Aha! I think I see my, Okay, let's print this part. So let's do that. And let's call this stuff. And print stuff. That's got to be where the error is, right? No, 0. Well, it returned a 0. Aha. Okay, let's try this. Print P 0, 0. And up here, I'm going to change this to, I'm going to get rid of that print. Let's actually comment on all of the stuff. Sorry for causing problems, but I think this is useful stuff because you can see how to fix stuff. And what did I say? I'm going to change this to VPython 3 because I've had some problems with this before. Okay, so now it's working. Okay, so that wasn't my fault. Okay, I don't know what the problem was, but it's working now. Okay, so now let's plot the probability density. So I'm going to say x equals 0, dx equals 0.01, and then I will say while x is less than a, first calculate the wave function. No, let's go and plot it. Let's say f1.plot. My x value is going to be x. My y value is going to be p of x 0. Let's call it t and put t equals 0. So that's going to plot a data point. Then I want to move to the next x value, so I can say x equals x plus dx, and then that should go through and plot all my values of the spatial, of the wave function at that time t equals 0. Okay, that's pretty nice. I'm pretty happy with that. Now, how do I animate that? What I need to do is to redo this thing. I need to update time and redo the thing. So how do I do that? Well, there's one quick trick I need to do down here. And that's up here, I'm going to say data equals an empty list. I'm going to plot the same thing, but I'm going to do it a different way. And down here, instead of plotting, what I'm going to do is to say data equals data plus my xy values that I want to plot. So it's going to be x p of xt. And this is kind of what's awesome about Python is I can have a function, I can plotting the value of a function. I'm calling that function in the plot. Now I do not want to do this line right here, so I'm going to delete that. This just goes through and adds all the data, all the values to this list called data. And then after the loop, I can plot it. So I can say f1.data equals data, and that will plot it. So if I run this, I should get the same thing. There you go. Now what I want to do is to do that again, but a whole bunch of times. So I'm going to make this, all this stuff, I want to redo a whole bunch of times. So let's just go up here and say while t is less than 5. And I don't know if that's a good time or not. We can always change it. One of the things I'm going to add, since I want it to animate, I need a rate statement. So let's say rate of 100. This will do 100, no more than 100 calculations every second. So this stuff's going to be indented. I do need to change one more thing because it's part of a loop. Oops. What the heck? And then, okay, that's fine. That's indented too. Up here, one of the things, if I go through this loop, it says while x is less than a. When I get to the end of the loop and I go back and do it again, x is already greater than a, so it's not going to do anything. So I need to reset the data, clear the data, and I need to reset x equals 0. Then I'll go through and plot the data and go back and do it again. Now the one thing I need to add right here is t equals t plus dt. And so then I can go do it until t equals 5. Now I think this will work. If it does, I'll be pretty impressed that it didn't make a mistake. And I think my step is just too small. Oh, can't find dt. That's why I was looking at, I was staring at the graph as I was like seeing, is it really moving? And it wasn't because I didn't finish. dt equals 0.01. Now run it. Okay, now let's fix this. So the scale here is going to, this is pretty awesome. Okay, the scale here is going to adjust to auto scale. So I can fix it. So it goes up to 1.3, it looks like. So let's, in my graph up here, let's say, comma, return, just put on the line, and I'll say y max equals 1.4. And I got to put the a in max. Look at that. And there you see a non-stationary state. It's oscillating back and forth. I think that's pretty cool. What's even cooler is the frequency of oscillation depends on the difference in energy. And this is a huge point in quantum mechanics. Different energy levels produce a oscillation, frequency oscillation of, that's where you get the delta E equals HF, right? We have omega, so we have H bar. That's where you see that comes from. That's super important. It's a property, it's a quantum property of matter. Matter at different energy levels oscillates at that particular frequency. And there you go. So I will include hopefully some links. Number one, the 1D square well. I'll include a thing about making animated graphs, and maybe something else. I'm not sure if I forgot something, but and the code for this. Okay. So I hope that helps. You can try a couple things that you could try. One, check and see if this is normalized. Is it normalized with respect to time? Two, is it normalized at t equals 0 and at t equals 1? And you can do a numerical integration of this and see. Two, what if I use different energy levels? What would that look like? Try that, E1 and E3, or E2 and E3, and see if the frequency of oscillation is indeed what you expect. So there you go. So I'm going to save this. I'm going to give you the link to the code, and that's that.